what we're doing really when we find the p-value is we're comparing it to what we call the rejection region or the critical region based on our alpha level. So when we have a left-tailed test, if this region is alpha, or a right-tailed test and this region is alpha, we want to see if our z-score is within that region. Or if there is a two-tailed test, we want to see if our z-score is within half of alpha. So we can do this by finding where that critical region is based on the alpha level. Okay, so if we have a left-tailed test, that means that all of alpha ends up to be right here. That means that if we use inverse norm of 0.01, our alpha level, that will give us the z-score that corresponds to that location. And when you put that in your calculator, you should get negative 2.3263. So with a 1% level of significance, we can compare if the z-score is smaller than negative 2.3263 or equal to negative 2.3263, then we can say that with 1% level of significance, we can reject the null hypothesis. In this one, we are looking at a two-tailed test. When it's two-tailed, this is 1/2 of alpha, and this is 1/2 of alpha. So if alpha equals 0.05, if I divide both of those by 2, then 1/2 of alpha would be 0.025. So this is 0.025 here, and this is 0.025. So if I do inverse norm, I can do it of 0.025, or I can do it of 1 minus 0.025. And I'll get the same exact thing. So if I do inverse norm of that, for this one, I'm going to get negative 1.95996, and for this one, I'm going to get positive 1.95996. So plus or minus 1.96 is the critical z-score for a alpha level of 0.05. So if I'm doing a z-test for the mean, I'm going to follow these steps. Check, make sure that your conditions are met. State your claims. What's your H0? What's your H alternative? Identify your significance level. What is your alpha? Find those critical values, or use the inverse norm. You can use the tables or inverse norm. Find those rejection regions. Find the z-score that you're going to compare to those rejection regions, and then decide to reject or fail to reject based on whether that z-score is within the rejection region. Okay, let's do it with this example. We are the employees at a construction company and a mining company claim that the mean salary of the company's mechanical engineers is less than that of one of its competitors, which is at 88,200. A random sample of 20, so that's n, found that the mean was 85,900, which is less. Assume that the population standard deviation is 9,500 and it's normally distributed. Okay, so it's random, it's normally distributed, we checked our claims. We got to find our null and alternate hypotheses. We are going to test the employee's claim that they think the engineers make less than the competitors. So the mean salary is less than 88,200. That means that the null hypothesis is greater than or equal to 88,200. From there, we know that the sample mean is 85,900. We know that population standard deviation is 9,500, n equals 20, and our alpha level is 0.05. So we can start by finding our standard error, which is going to be 9,500 divided by the square root of 20. 9,500 divided by the square root of 20 is 2124.264,579. Now we need to use that to find the z-score. And keep in mind that this is a left-tailed test. This is our alpha level. Alpha is equal to 0.05. That means that our z at this is going to be equal to negative 1.96 by doing inverse norm of 0.05. That's not right. I just did it. I wrote down the wrong number. It's not that. It is negative 1.64485. So we have to see what our z-score is, which is equal to our sample mean, 85,900, minus population, 88,200 mean, divided by our standard deviation, 2124.264,579, which gives us a z-score of negative 1.082727. Now what we do is we compare where this is in relation to our alpha level. This is our alpha to 0.05, and this z-score is going to be somewhere over here, which is not in the rejection region. Which means we fail to reject. With, or actually let's say this, let's say there is not enough evidence to support the claim that the mean salary at this company is less than $88,200.